This video is sponsored by Cyfrin. Follow the course on Cyfrin Updraft for better tracking, quizzes, prove your knowledge, and join a community of over 50,000 Web3 engineers ready to help you out and answer your questions. Welcome to the course for Curve V1 AMM. This course is for advanced Solidity developers who have experience with Foundry. To fully understand this course, you must also know the math of constant product AMM and constant sum AMM. These are the prerequisites, the must-haves. We also have some optional prerequisites. In the course, we'll sometimes compare Uniswap B2, B3, and Curve V1. In other parts of the course, I'll also mention about some basic DeFi stuff, for example, like stablecoins such as DAI and USDC. So having a basic familiarity of DeFi will help. And finally, there are some optional lessons where I would use Python to show you some of the math of Curve V1. So these are all nice to haves, but are not required to follow along the course. Why take the course? First of all, understanding Curve V1 might give you some ideas for a new AMM design. It's not just Uniswap B2 and B3 that are AMMs. We also have other AMMs, and by taking this course, you'll get a better feeling for how you might construct a new AMM. It might also help you in audit contests and bug bounties. And the last reason why you should take this course is because this is a prerequisite to understand Curve V2. What will you learn in this course? You'll learn the math and algorithms for Curve V1. Curve V1 is written in Viper, and we'll do a code walkthrough of the Curve V1 contract. So you'll gain some experience reading Viper. There are exercises and solutions written in Foundry, so you'll have some hands-on experience testing with Foundry. I'll be your instructor, Taz. So you might be asking, who am I to teach you this course? Well, I've been a software developer for more than a decade, and I've been a smart contract developer for more than 5 years. I also teach about smart contract programming on my YouTube channel, Smart Contract Programmer. And I am the author of the websites Solidity by Example and Viper by Example. The GitHub repo that we'll be using in this course is called Advanced DeFi 2024. For the course for Curve V1, scroll down and look for a markdown file called curvev1.md. Click on this. This will take you to a markdown file that shows all of the links that you'll need in this course. Inside this file, it lists the prerequisites, which we already have discussed, and it also lists the tools that you'll need. The tools that you'll need is Foundry, and optionally, if you want to follow along the optional Python examples, install Python and also Jupyter Lab. For each lesson, watch the videos on Cyfrin Updraft. And for the exercises, you can find the link under the section called Topics. So, scrolling down, we have a section called Topics, and then under here, you'll see some of the links to the exercises and the solutions. Now, there are other links inside this markdown file. Some of them link to the code that is used inside the videos, and other ones will link to additional notes and graphs. If you have further questions, you can navigate to GitHub discussions under this repo. So, scrolling back up, under this repo called Advanced DeFi 2024, click on Discussions, and then you can ask your questions here. To do the exercises in this course, you'll need to git clone this repo. And to do that, click on Code, and then copy this URL. Inside the terminal, type git clone, and then paste the repo. Once the repo is cloned into your computer, next cd into Advanced DeFi 2024. The exercises are written in Foundry. So to do the exercise, you'll first need to install Foundry. If you have not done so, copy and paste this command to install Foundry. Now, this command only works for Linux. Once Foundry is installed, let's do a quick check to make sure that the contracts, which are used for the exercises, compile. The contracts are located under a folder called Foundry, so say cd Foundry. And inside here, we'll do a quick check by compiling the contract, forge build. And that contract compiled successfully. So if you made it this far, congratulations, you're now ready to do the exercises. Inside this folder, the exercises and the solutions are located under the test folder. The exercises and solutions are organized by the name of the DeFi protocol. For example, here under Uniswap B2, you'll see a folder called exercises and solutions. The same goes for Uniswap B3, and for this course, we have Curve V1. There's a folder called exercises and a folder called solutions. Exercises will contain some starter code, and inside here, you'll write your code. If you get stuck or if you just want to see the solution, then open the solutions folder. Inside it, you'll see some contracts which will contain the solution to the exercises. Now to execute the exercises or to just compile the contract inside this Foundry folder, what you'll first need to do inside your terminal, first go into the Foundry folder. So from the project group, I'll cd into the Foundry folder, cd Foundry. To compile the contract, type forge build. If you want to execute the exercises or the solutions, what you'll need to do is follow this command. First, you'll need to set up the environment variable for fork URL. This will be the URL that will be used to execute your code against the mainnet fork. And then afterwards, either to execute the exercises or the solutions, you'll have to type this command in. So let's go through an example. First, I'll set up my fork URL. I'll type fork URL equals, and then paste the fork URL. This URL I signed up and then got from Alchemy. Next, let's execute one of the code inside Curve V1 solutions. Let's execute the code inside Curve V1 swap.test.sol. To do this, you'll have to type forge test followed by fork URL, and then the environment variable that we set, fork URL, and then the path to the test is match path test Curve V1 solutions, and the name of the contract is Curve V1 swap.test.sol. And if you wanted to also print out the console logs, then you'll type -bbb. Okay, that executed two functions, test exchange and test get dy underline. I'm not going to open this file because I don't want to show you the solutions, but let's say that we only wanted to execute this function called test exchange. So what you can do is we'll start with the same command as the previous example, and then we type -- match test. The name of the test is test exchange. This will only execute the test called test exchange inside the contract Curve V1 swap. And the same goes if you wanted to execute one of the contracts inside the exercises. What you'll have to do one of the exercises is open exercises, let's say Curve V1 swap.test.sol, and then you write your code inside here. And to execute the code inside here, what you'll do is, inside your terminal, you will execute a similar command to this one, and instead of solutions, the path to the test will be under exercises. And obviously the test fails because the code inside the exercises are incomplete. It is your task to fill out the code inside the contracts under exercises. So this is how the exercises and solutions are organized inside this repo. For those of you who are new to DeFi, here I will give you a quick explanation of USDC and DAI, which I will be using in this example. USDC and DAI are both cryptocurrencies that target $1. This is called a stablecoin. There are different mechanisms so that the price of the stablecoin floats around $1. We will not discuss here, and this will be a topic for another DeFi course. With that said, let's take a look at an example of swapping USDC for DAI. Using Uniswap V2, let's say that you wanted to swap 1000 USDC for some amount of DAI. Currently, the best deal that you can get is 1000 USDC and you'll get 996 DAI. These two coins are stable coins where the price are close to $1. So if we were to swap 1000 USDC, we expect that the amount of DAI that we can get is also close to 1000. However, this is not the case. Here we're losing $4 if we were to swap this 1000 USDC on Uniswap V2. And of course, if we were to use Uniswap V3, we will get a better deal. This is because Uniswap V3 has concentrated liquidity. However, before Uniswap introduced concentrated liquidity, the option to swap USDC for DAI was either on Uniswap V2 or on another AMM called Curve. On Curve, if we were to do the same swap, 1000 USDC for some amount of DAI, then we would get 999.92 DAI. This is a better deal than swapping on Uniswap V2 where we lost more than $4. Here we're losing less than $1. Curve V1 is an AMM that is optimized for swapping tokens that should have similar prices, for example USDC and DAI, or USDC and USDT. They are all stablecoins that target $1. Another example is ETH and STETH. Both of them have a similar price. so they should swap close to 1 to 1. If you put in 1 token to the Curve AMM, you should get back approximately 1 token out. How is Curve V1 different from Uniswap V2 and Uniswap V3? For this comparison, we'll consider the case when we're swapping between USDC and DAI. Let's start with the language. Both Uniswap V2 and Uniswap V3 are written in Solidity. On the other hand, Curve V1 AMM is written in Viper. As you saw in the previous video, the slippage on Uniswap V2 is high. For example, if we tried to swap 1000 USDC, then we saw that we only got 996 DAI on Uniswap V2. On Uniswap V3, it introduces a concentrated liquidity, so the slippage will be low. If we were to swap 1000 USDC, then we'll probably get something close to 1000 DAI. And we also saw in the previous video that slippage on Curve V1 is also low. We saw that if you were to swap 1000 USDC, then we got 999.92 DAI. Both in Uniswap V2 and in Uniswap V3, it supports 2 tokens. For example, in Uniswap V2, we saw an example of a USDC DAI pool. And also in Uniswap V3, it can only have 2 tokens. However, in Curve V1, it can have 2 or more tokens. For example, on the user interface of Curve Finance, you can see over here that there's a pool with 3 tokens, DAI, USDC, and USDT. And if you scroll down, there are some pools with 2 tokens, and there are other pools with 4 tokens. Another difference between Uniswap AMMs and Curve AMM is how liquidity is added and removed. For Uniswap V2, when we add liquidity, both tokens must be sent. And when we remove liquidity, both tokens will come out. How about in Uniswap V3? In Uniswap V3, it depends on the price range where you're adding liquidity and the current price. If you add liquidity to a price range that is outside of the current active price, then you can only add 1 token. If you're adding liquidity to a price range that includes the active price, then you must add both tokens. And for removing liquidity, this is also the same. When you remove liquidity, if your liquidity position is outside of the active price, then you can only withdraw 1 token. However, if the current price is in between your liquidity position, when you remove liquidity, you'll get both tokens. However, in Curve V1, you can specify which tokens you want to withdraw. It can be 1 token, it can be all tokens, or it can be somewhere in between. For example, inside the Curve 3 pool that consists of DAI, USDC, and USDT, let's say that we have 100 LP tokens and we only want to withdraw DAI. Then this is possible. We can also only withdraw in USDC or in USDT. We can also withdraw all of the tokens in a balanced way, or we can specify how we want to withdraw the tokens. For example, maybe we only want DAI and USDT and not USDC. On Uniswap V2 and V3, there is no fee that is charged when we add or remove liquidity. However, in Curve V1, we can both add and remove liquidity in a way that results in the pool's balance being imbalanced. For example, if we had 100 USDC, 100 DAI, and 100 USDT in a Curve pool, and we decided to withdraw all of our liquidity in DAI, then the balance of the tokens after removing liquidity will be imbalanced. In this case, Curve will charge a fee on imbalance. And this is the same for adding liquidity. Let's say that the Curve V1 pool is balanced, and then we add a lot of DAI. This will make the balance of the coins in the Curve V1 pool imbalanced, and in this case, imbalance fee will be charged. And the last big difference between Uniswap and Curve V1 is how swap fees are charged. Both in Uniswap V2 and V3, swap fees are charged on token in. However, in Curve V1, swap fees are charged on token out. Okay, so these are some differences between Curve V1, Uniswap V2, and Uniswap V3. In Uniswap V2, the curve of the AMM, the constant product curve, is given by x times y equals k. Here in this example, instead of using k, we'll use d over 2 squared. We also have the constant sum, which is given by the equation x plus y equals d. The Curve V1's AMM curve is a curve that sits in between the constant sum and the constant product. The equation is given by this equation, which looks complex. And it looks like, if we graph this, it looks like this. When the tokens x and y are in imbalance, then we can see that it looks sort of like the constant product curve. When the tokens are in balance, then it looks more like the constant sum. In other words, when the amount of token x and amount of token y in this pool are close to each other, then you can swap one token for another close to 1, simulating the constant sum curve. However, when the tokens are imbalanced, it behaves more like the constant product curve. Now, in this curve B1's curve, there's a parameter that defines how flat this curve is. Inside the white paper and also inside the code of Curve V1 AMM, this parameter is called A. When we increase A, we can see that the curve's B1 curve becomes more flat and it behaves more like the constant sum. And when this A decreases, it behaves more like the constant product. So the curve's B1 curve is given by this complex equation. Let's break this down and see how to actually recreate this curve. Our goal is to create a curve that sits in between the constant product and the constant sum. So let's start by combining the constant product and the constant sum. So first I'll copy this constant product curve, and then to this, let's add the constant sum curve. So on the left side of the equation, I'll add a x plus y, and on the right side, I'll add a d. So this x plus y and d is the constant sum curve. What we just did over here is took the constant product, and to this, we also added a constant sum. X times y equals d over 2 squared, that's the constant product, and x plus y equals d, that is the constant sum. And notice that not much has changed. The curve still looks like a constant product. Now before we move on, notice here that we have a d over 2 squared, and the next term is a d. Let's multiply this d again by another d, so that on the right side of the equation, we have terms in d squared. So I'll multiply this by a d, so we will get d squared. And since we multiply this side by a d, we also need to multiply this x plus y by a d. Okay, and now it sort of looks like a curve that is in between constant sum and constant product. So remember that when we increase this a parameter, this curve should look more like the constant sum, and when we decrease it, it should look more like the constant product. So I'll add the a term to the part of the equation that describes the constant sum, and also do the same on the right side of the equation. And when we increase this a parameter, now our curve starts to look like a constant sum. If we decrease it, it looks more like the constant product. And at a equals 0, we get exactly the constant product. Again, let's increase the a term. So from here, how can we get a curve that looks like the curve B1's curve? Well, first of all, notice that our curve right now crosses over the x-axis and also the y-axis. This means that this curve describes token balance that are negative, but that is not possible. Token balances has to be greater than or equal to 0. So we want this green curve to be within the x-axis and also within the y-axis. To do this, we can multiply both sides of the constant sum equation by a x and a y. So for example, if we multiply this side by a x, and then we also multiply this side by a x, now notice that our green curve doesn't cross over the y-axis. It stays to the right of the y-axis. And we can do the same trick so that this part of the green curve doesn't cross over the x-axis. So multiply by y, and then multiply by y over here as well. And now, what do we get? Now it kind of looks like a curve that is a constant sum, but without crossing over the x-axis and the y-axis. When a is equal to 0, we get the constant sum, and when a is equal to 1, we get this curve. So right now, our curve is really sensitive to the parameter a. To make this less sensitive to the a parameter, what we have to do is divide this x times y by a d over 2 squared. And the same goes on this side of the equation. Divide this x times y by d over 2 squared. And what do we get? If we increase a, now we get a curve that looks like curve B1's curve. And if we increase this a parameter, it looks like the constant sum. And if we decrease it, it looks like the constant product. So what we just did was recreated the curve B1's equation, starting from constant product and constant sum. But why did we multiply this part of the equation and this part of the equation by x times y divided by d over 2 squared? What does this part of the equation actually do? To give you a quick explanation, what it does is when the token balances of x and y are equal, then this x times y divided by d over 2 squared is equal to close to 1. For example, we can see that x times y divided by d over 2 squared will exactly be equal to 1 when both x and y are equal to d over 2. And when x and y are not equal to d over 2, then this term is less than 1. And when x and y are imbalanced, then this term approaches 0. So what this x times y divided by d over 2 squared is doing to this part of the equation and this part of the equation is saying that when x and y are close to d over 2, then apply this part of the equation, so apply the constant sum part of the equation, and when x and y are not in balance, then this part approaches 0, so the dominating factor of this equation becomes the constant product. In other words, when the amount of token x and amount of token y are close to each other, when they are balanced, the curve will behave like the constant sum. And when the amount of tokens are not in balance, then they behave more like the constant product. And that is why you see that when the tokens are in balance, our curve looks like the constant product at the edges. In the previous video, we graphed Curve's V1 curve onto D. What made this equation work nicely so that we have a curve that is in between a constant sum and a constant product was the term x times y divided by d over 2 squared. In this video, we'll take a look at this term x times y divided by d over 2 squared in 3D. So when we graph this, we get a three-dimensional surface. The inputs are all of the points on the xy plane, and the output is described in the z-axis. So what we get is a two-dimensional surface in 3D. Now what we're interested here is how this function behaves on the points of Curve's V1 curve. But before we do that, let's first plot this x times y divided by d over 2 squared for all of the points on the constant product. So what we're going to do is take all of the points x and y that satisfy x times y equals d over 2 squared and take those points and then evaluate this equation, which is equal to x times y divided by d over 2 squared. When we do that, we get a blue line on this 2D surface. And for this, the z is always equal to 1. And this is because if we take all of the points x and y that satisfies the constant product, x times y equals d over 2 squared, and then we plug it into this equation, since x times y is always equal to d over 2 squared, this function will always evaluate to 1. So this is why for z we always get a 1 when we look at the points on the constant product curve. How about the points on the constant sum curve? And what do we get? We get an arc that touches 1 and decreases to 0 as y goes to 0, and also decreases to 0 as x goes to 0. Okay, what kind of line will we get on this 2D surface if we evaluate this equation for the Curve's V1 curve? This is described in the line orange. On this graph, I'll also put the point d over 2, and z equals to 1. This is shown in purple. And what we can see from here is that the x times y divided by d over 2 squared, for the points on the Curve's V1 curve, we get this orange line, and what it looks like is when x and y are close to d over 2, then z is equal to 1 on this orange line. And as x and y become imbalanced, then this orange line approaches 0. For example, we can see that as x increases and y decreases, z, given by this orange line, decreases to 0. And the same goes for the other way. As y increases and x decreases, we can see that this orange line also decreases to 0. In summary, we analyzed how x times y divided by d over 2 squared behaves in 3D. And what we found out was that when x and y are close to d over 2, then this equation is equal to 1. And as x and y become imbalanced, then they approach 0. Here I'll explain more about Curve V1's equation that you'll see in the white paper. In the previous video, we looked at the equation for 2 tokens, but inside the white paper, the equation is for n tokens. This n is a number that can be greater than or equal to 2. To begin with, we have the equation for the constant sum. Sum all of the token balances from I equal to 1 to I equal to n, and this must be equal to d. For example, for 2 tokens, this will be x plus y equals to d. And we also have the constant product, multiply all of the token balance from I equals to 1 to I equals to n. And again, for 2 tokens, this will be x times y equals to d over 2 raised to the 2. And then we have the Curve V1 equation, which is a composition of the constant sum and the constant product. Furthermore, the constant sum part of this equation is multiplied by this symbol called chi, and then multiplied by d to the n minus 1. And this chi is equal to the a parameter that controls how flat this Curve V1's curve is, and then multiply by all the token balances, and then divide by d over n, and then raise it to the power of n. Again, going back to the example of 2 tokens, we saw that this was equal to x times y divided by d over 2 raised to the power of 2. This is the equation that you'll see in the white paper of Curve V1. In our example, we saw this equation for 2 tokens, and this equation over here is a generalization of that equation. Now it's the same equation as above, but another equation that you'll see in the Curve white paper is given by this form. So in the rest of the video, I'll show you how to derive this equation, starting from this equation. So to begin with, I'll copy all of this equation, and then I'll paste it here. Next, I'll replace this symbol called chi with the actual terms. And to be clear, I'll highlight this as orange. And then I'll paste it here. And the same for over here. Okay, so to go from this equation to this equation over here, all we have to do is divide both sides of the equation by d divided by the product of all the coins. So let's expand this equation. On the left side, we multiply this, and the same with the right side. Let's start by simplifying the left side of the equation. So first of all, I see a product of all the tokens on the bottom, and I see the product of all the tokens on the top over here. So these two will cancel out. Next, I see a d raised to the power of n, and over here I see a d raised to the power of n minus 1, and then multiply this by a d, so this part will be d raised to the power of n. So this will cancel out with this over here. Okay, so the first term that is left is a times n to the n, and then we have this constant sum. Next, we have a plus, and then the product of all the token balances on the bottom and the product of the token balances on the top will cancel out, and the second term will become a d. Okay, so this is the left side of the equation. How about the right side of the equation? On the right side, as a denominator, we have the product of all the token balances, and for the first term, we have a product of all the token balances as a numerator, so this will cancel out. Next, I have a d raised to the power of n over here, and then it is multiplied by d raised to the power of n, so these two cancel out. So the first term is a multiplied by d, and then multiplied by n raised to the power of n. Okay, and then for the next term, we have a plus, and then we have a d multiplied by d raised to the power of n, so this will become d raised to the power of n plus 1. And on the bottom, we'll have this product. And furthermore, this product is multiplied by n to the n. Okay, let's put all of this together. So we get this equation after multiplying both sides of the equation by d divided by the product of the token balances. You can compare each of these terms, and you'll see that they are the same. This is the other form of equation that you'll see in the Curve's V1 white paper. Both in Uniswap V2 and Uniswap V3, we have an explicit equation for liquidity and for the amount of tokens that will come out from a swap. For example, in Uniswap V2, the amount of tokens to get out of a swap and the liquidity can all be solved from this simple equation. And here's the explicit equation for the amount of token Y to come out if we were to put in dx amount of token X. Likewise, in Uniswap V3, we can solve for liquidity and also the amount of tokens to go out during a swap by using this equation. For example, here are the equations that you'll use to calculate the amount of token X and amount of token Y given the liquidity and the price ranges. However, in Curve's equation, it's really difficult to come up with an explicit equation for the amount of tokens to come out during a swap, and also an equation to calculate liquidity. Here's the equation that is used in Curve V1 to calculate the amount of token that will go out during a swap, and also to calculate liquidity. And just by looking at this equation, you can already see that it might be difficult to come up with an equation for the amount of token that will come out, and another equation that will calculate liquidity. Even if we consider the case for 2 tokens, the equation still looks complex. And again, it looks difficult to come up with an equation for the amount of tokens that will come out during a swap and also for liquidity. So we saw that there might not be an easy way to find the equation for x, y, or d. In Curve's equation, this d sort of represents liquidity. The solution that Curve uses to find x, y, or d is to use a mathematical technique called Newton's method. So what is Newton's method? Newton's method is a mathematical technique to find the solution for the equation f of x equals 0. So the goal is to find x where the function f of x will evaluate to 0. Don't worry for now if this sounds abstract. In the next video, we'll go through a Python example. The way this algorithm works is we first start with a guess of what this x might be so that f of x will be equal to 0. So for example, let's say our initial guess is x0. Next, we're going to run a while loop until when we feed this x sub n into the function f, it will evaluate to 0 or something really close to 0. So inside the while loop, we say the next x sub n plus 1 is equal to, take the current x sub n, and then from this minus evaluate f at x sub n, and then divide this by the derivative of x evaluated at x sub n. And if everything goes well, this x sub n plus 1 will usually be a better estimation of where f of x will be equal to 0 than x sub n. Now, there are cases where Newton's method does not work well. If you're curious for more information, I'll put a link in the course. And then next, we evaluate the difference between x sub n plus 1 and x sub n. If this difference is really small, then we return x sub n plus 1. In other words, when we plug this x sub n plus 1 into this function f, we'll get a number that is really close to 0. Otherwise, if x sub n plus 1 minus x sub n is not a small number, then we move on to the next iteration of the while loop, so we set x sub n equal to x sub n plus 1. And that is the basic idea for Newton's method. Let's see how this is used in Curve to calculate x, y, and d. For example, how does Curve use Newton's method to find y? To begin with, we first need to set up a function. For this example, we'll use the equation for n equals to 2. So I'll copy this, and then we'll paste it here. And we'll define f of y be equal to this part of the equation, and then we minus the right side of the equation. So if we can find a y where this equation evaluates to 0, then this means that then we found a y where this equation is satisfied. So we set up our equation to be this, and we use the Newton's method to find y where f of y is equal to 0. Let's look at another example. Let's say that we wanted to find d. Again, this d sort of represents liquidity in Curve, and use Newton's method to find d. The equation is a little bit different from the first one. The right side of the equation is the same, but the input for the function is different. Here we're solving for y, and over here we're solving for d. But on the right side of the equation, we still use the same equation. And using Newton's method, we find d where f of d is equal to 0. In the next video, we'll go over these examples using Python. Let's go over a simple example of Newton's method using Python. So let's say that we have a function, def, I'll call this f, takes in a single input x, and let's say that our simple equation is x squared minus 2. So using Newton's method, we're going to try to find the x such that when we evaluate x squared minus 2, then it equals to 0. Now to use Newton's method, remember that for Newton's method we had x, the new x, was equal to the current x minus f of x divided by the derivative of f prime of x. So we have our function f, we also need a derivative. In this case, the derivative is simple, so let's call this def df for a derivative of f. The derivative of the function x squared minus 2 is simply return 2x. So we're going to use these two functions and then apply the Newton's method. So let's first write a general algorithm for the Newton's method. I'll call this def, and I'll name this function f solve. Solve the function f. So this is our function that's going to apply the Newton's method, and for this function, it's going to take in several inputs, the function f, and the derivative of f, we'll call this df, and our initial starting point for x, I'll call this x0. Next, we'll put a number of iteration, the number of max iteration to apply Newton's method, I'll call this n, and lastly, I'll pass in an input, I'll name this delta, and this will be a number so that when we apply this equation, so let me rename this variable, I'll call this x1 and x0, and put an x0 over here and x0 over here. So this delta will be a number that when we compare x1 and x0, and when they are small enough, smaller than delta, then we'll return this x1. Inside this Newton's method, so I'll say for I in range of n, we'll write some code over here later, and if this function does not return a solution within this n iteration, then we'll throw an error. So I'll type assert false, cannot find solution. Okay, so next let's write the Newton's algorithm for each iteration. And for debugging purpose, let's also print I and x0. So first we'll apply this algorithm. So I'll just copy this and then paste it here. x1 is equal to x0 minus f of x0. This f comes from the input divided by f prime. Let's call this df, which also comes from the input. And this is how we get our x1. Next, we'll need to return x1 if the distance between x1 and x0 are smaller than delta. So say if the absolute value, abs of x1 minus x0 is less than or equal to delta. If the difference between x1 and x0 are small enough, smaller than or equal to delta, then we'll say that we found a solution where when we evaluate f of x1, this will be really close to 0. So say return x1. Else, we'll need to continue the iteration. So say the new x0, the x0 to be used for the next iteration, we'll set this equal to x1 that we just calculated from here. And this completes our Newton's method. Now, if you want to write a robust Newton's method, then there are some edge cases that you'll have to worry. But for the sake of simplicity, we'll keep this algorithm simple. Okay, so let's now use Newton's method to find an x where x squared minus 2 is equal to 0. So let's say x is equal to f solve. We'll solve for the function f, and the df is defined over here, df. And next, our initial guess, let's put a 1 over here. And for iteration, the number of max iteration that we're willing to accept for this Newton's method to find the solution, let's put this to 1000. And delta. When the difference between x1 and x0 is small enough, it will return x1. So this delta, let's say, is 0.001. Okay, next, after it finds a solution, if it does find a solution, if it does not find a solution, then it will throw an error and this whole execution will fail. So let's say that we found a solution. Let's actually print this solution. So we'll evaluate f of x. And what we expect here is that this number to be equal to 0 or something really small. So let's say print f of x is equal to, and let's also print the solution, print x is equal to x. Let's now execute this Python code. So as you can see, it ran 3 iterations and then found the solution. And according to Newton's method, the solution is equal to 1.41421 and so on. And also, when we took this solution and then evaluate f of x, we get a really small number that is really close to 0. So this was a simple example of Newton's method. Let's now apply this same algorithm, Newton's method, on Curve's equation to calculate y and to calculate the number d. Okay, let's start by defining the equation for Curve using Python. So let's call def f. For this function, we'll put in several inputs, x, y, the amplification factor a, and the liquidity d. And the function is return x times y plus k. I'll do this lowercase k. And where this k is equal to a times x times y divided by d over 2 to the square. Okay, and then we have k times d times x plus y. So this is the left side of the Curve's equation. And the right side is minus d over 2 square minus k times d to the square. Okay, next I'll define some parameters that we'll be using for this example. Let's say n is equal to 100. This will be the max iteration. And delta, let's set this to equal to 0.0001. And let's say that we have x equals to 120, y equals to 90, a is equal to 10, and d is equal to 200. For the first example, we'll use Newton's method to find d. So given we know what x is, we know what y is, and we know what a is, then we'll use Newton's method to find d. Def f, I'll call this fd. It's going to take in a single input, the d that will be passed into the Newton's method. Then it's going to return f of, f is the function that's defined over here. The x is already known, so this x will be used. Y is also known, and a is also known. So x, y, and a, these 3 parameters will be used for this function. xya, and d will come from the Newton's method. Okay, next we need to calculate the partial derivative of this function with respect to d. So I'll say df, I'll name this dd. It's going to take in a single input, d. It's going to be passed from the Newton's method. And here's the partial derivative of this function f with respect to d. I'll briefly cover how I calculated this in the next video. Or you can also use paper and pencil to manually calculate the partial derivative. Okay, let's now apply Newton's method. So let's say d is equal to Newton's method f solve. It's going to take in the function f of d. Next, it's going to take the derivative of this function, df dd. The next parameter is the initial starting point for the Newton's method. And for this initial starting point, we will use this d over here. Next is the number of iteration, the number of max iteration. You'll pass n, which is equal to 100, and then delta, which is equal to 0.0001. So let's say that Newton's method was able to find d given these parameters, x, y, and a. It calculates d where it satisfies this equation, where this is equal to 0. So let's evaluate f of d passing in this d that was found by Newton's method. And then let's print both of these out. Print d, and then print f of d passing in d. So here I'll say f of d, and then remove this. Okay, let's execute this code. And notice that using Newton's method, we were able to find d that satisfies this equation given these three parameters in 4 iterations. So according to Newton's method, the d that satisfies the equation is equal to 209.895984 and so on. And when using this d and then evaluating the function f of d, it returns a number minus 1.1645 and so on, raised to the power of minus 10. It's a really small number that is close to 0. Okay, for the next example, let's again use Newton's method to calculate y given these parameters. Given that we know x, given that we know a and d, what is the value of y that will satisfy this equation so that it equals 0? Okay, so let's start by defining a function that takes in a single parameter of y and then calls this function. So I'll just copy this, paste it here, and then I'll call this f of y. For the input, it will take in a single input of y that is calculated from Newton's method, and then we'll call this function, which is this function over here. Okay, and next we need to find the partial derivative of this function f with respect to y. So say def, call this df of dy. The input will be y, and the partial derivative of f with respect to y is given by this formula. Again, I use Python to calculate this partial derivative, but you can also calculate it using paper and pencil. So once we define the function f and then the derivative of f, next let's use Newton's method to find y. So first I'll copy this code and then we'll modify it. So paste it here. The output will be a y. The function that we're feeding is f of y. The derivative of this function will be df dy. And for the initial guess, how about we put in this x value? So let's put an x here, and the number of iteration will be n, and delta will be the same, which is equal to 0.0001. So we'll print out y that was returned by Newton's method, and then we'll also evaluate f of y, passing in this y that was returned by Newton's method, f of y, and passing this y. Okay, let's execute the function, then scroll down. So using Newton's method, given that we know x, a, and d, the y that satisfies this equation so that this part is close to 0 is y is equal to 90. And when we evaluate f of y with this value, it returns 0.022 and so on. So those were some examples of using Newton's method to calculate d from the curve's equation and also to calculate y from the curve's equation. Here I'll briefly explain how I use Python to calculate the partial derivatives for the curve's equation. The library that I used is called sympy. The first thing that I did is import this sympy, and next using this library, I defined the curve's equation, And to get the partial derivative of this function with respect to d and with respect to y, all I had to do was call a function that is provided by this sympy library called diff. Here saying differentiate the function f with respect to d, and I get df dd. Likewise, if I differentiate this function f with respect to y, I get df dy. And then I printed these out. And when I do this, what I get, the results are over here. df dd is equal to this, and df dy is equal to this. I copied these code and then used it in the previous video where we used it in the Newton's method. For Curve V1, there is only one contract that the user interacts with when they swap, add liquidity, or remove liquidity. Now let's take a look at the user interface for Curve. When we scroll down, we can see that there are different pools. Here we have the 3 pool, and then next we have the USDE, USDC pool, and scrolling down further, we have the STETH pool. Most of these contracts are a variation of a base contract called StableSwap. For example, the 3 pool contract is called StableSwap 3 pool, and the STETH pool contract is called StableSwap STETH. So if you understand one of the StableSwap contracts, it won't take you long before you understand the other Curve V1 AMMs. Let's take the example of 3 pool and STETH. These two are a variation of a contract called StableSwap. Now notice the difference that over here we have 3 tokens. So 3 tokens will be inside a single contract, and over here we have ETH and STETH. 2 tokens will be inside a single pool contract. Let's take a look at the contract for 3 pool, which is called StableSwap 3 pool under Curve Contracts Pools 3 pool. The first thing that I want to mention here is a constant called n-coins. This tells how many tokens this pool will support. Since 3 pool is DAI, USDC, and USDT, it supports 3 tokens. Hence, n-coins is set to 3. The reason why I'm mentioning this here is because this will affect the interface that you'll need to declare when you call Curve V1 AMM. For example, if you wanted to call the 3 pool, let's take a look at the function add liquidity. Inside the function add liquidity, you can see over here that amounts is a fixed size array of size n coins, where n coins is equal to 3. So when you declare an interface to interact with the StableSwap 3 pool, you'll need to make sure that this fixed size array is of size 3. In comparison, let's take a look at how the function add liquidity is defined for the STETH pool. The StableSwap contract for the STETH pool is located under Curve Contracts, Pools, STETH, and the name of the contract is called StableSwap STETH. The first thing that I want to show you is n-coins. So scrolling down, here it is. The constant n-coins is defined to be 2. And this is because this pool contract holds 2 tokens, ETH and STETH. Now, let's take a look at the function add liquidity. Okay, here's the function add liquidity. And notice that amounts again is declared as a fixed size array of size n coins, where n coins is equal to 2. To summarize what we've seen so far, Curve V1 AMMs is a variation of a contract called StableSwap. Each pool can hold up to any amount of tokens. For example, the 3 pool holds 3 tokens, and the STETH pool holds 2 tokens. And the input parameters are slightly different for each pool. So when you interact with the StableSwap contract, you'll need to actually look at the pool contract that you want to call and make sure that you define the interface correctly. The StableSwap contract can hold any number of tokens. For example, the StableSwap 3 pool contract is a contract that manages the tokens DAI, USDC, and USDT. Another example that we saw was the STETH pool, which holds 2 tokens, ETH and STETH. However, all of the StableSwap contracts will have 5 functions that are common: exchange, add liquidity, remove liquidity imbalance, and remove liquidity 1 coin. The function exchange is used to swap tokens, add liquidity to add the tokens to the pool, and for removing liquidity there are several variations: remove liquidity imbalance, and remove liquidity 1 coin. Remove liquidity will give back the liquidity providers all of the tokens. Remove liquidity imbalance will give the user an option to specify how many of each token they wish to get back, and remove liquidity 1 coin allows the user to specify the token that they want to get back as a single token. There's a common pattern for the way the codes are executed when the functions exchange, add liquidity, and some of the functions for remove liquidity are called on the StableSwap 3-pool contract. The pattern that you'll see throughout the code inside these functions are that they first calculate the A parameter and then calculate the liquidity D. For example, take a look at the outline for the function exchange. Inside this outline, we can see over here that it calculates A and then it calculates D. Let's take a look at another example. Inside the function add liquidity, it first calculates A and then it calculates the liquidity D. And then for remove liquidity, it doesn't need to do this, since the amount of tokens that need to be sent back to the liquidity provider only depends on the LP shares that are burnt and the total LP supply. However, it is different for remove liquidity 1 coin. So here we have the function remove liquidity 1 coin. And again, we can see that it first calculates the A parameter and then calculates the D parameter. Why does it do this, and what is the relationship between the A parameter and liquidity D? How does the change in A parameter affect the liquidity D? The reason why that we see a pattern of calculating the A parameter before calculating the liquidity D is because in order to calculate liquidity D, we first need to determine what the current A parameter is. Usually the A parameter is a fixed number. However, an admin can decide to set a new A parameter. Afterwards, the current A parameter will start updating towards the new A parameter. This change will take over time. While this A parameter is going through an update, the liquidity D may change. So let's see how this A parameter will affect the liquidity D. Here you're looking at an example graph of the Curve V1's equation in pink. Now Curve V1 can support multiple tokens. It can support 2 tokens, 3 tokens, 4 tokens, and so on. To graph this equation for 3 tokens, we need a 3D graph. And to graph this equation for 4 tokens, we will need a 4D graph. And of course, that is impossible, so we'll keep this example simple and say that the pool has 2 tokens. In this case, we can graph this equation on a 2D graph. So this is what you're seeing. Think that the pool has only 2 tokens. Now, let me explain how the A parameter will affect the parameter D. So let's say that we have some token balance, x0 and y0. The point x0 and y0 has to be a point on this pink curve. So I'll move this point so that it will be somewhere on this pink curve. Okay, and then I'm going to zoom in. So let's say that the current token balance in this Curve V1 AMM is over here. We can represent the token balance after a swap. For example, if token X went out and token Y came in, then this point will move up towards the left. And if there was another swap where token X came in and token Y went out, this point will move down and to the right. However, this blue point must be on this pink curve. Now, let's see what happens when the A parameters change. So let's say that the current token balance is over here, and then the admin decided to update the A parameter. The change in A parameter will take some time. So let's say that the admin set the A parameter to something higher. And now notice that the token balance is no longer on this pink curve. To make sure that this Curve V1's equation, given the A parameter and the token balances go through this blue point, what we need to do is find liquidity D such that this pink curve will go over this token balance. So to do that, let's adjust this D parameter. So let's move this liquidity D up, and we'll move it until we can see that the token balance will be on this pink curve. Okay, I think that's the best approximation. So at this point, we can see that the liquidity D is now 51.5. What happened was when the A parameter changed from 1 to 6, the shape of this pink curve also changed, and the token balance was no longer on this pink curve. To put this point back on the pink curve, what we had to do is find the liquidity D so that this pink curve will again go through this blue point. So that is why inside the code, it will first calculate the A parameter and then afterwards calculate the D parameter. What it's doing is, given the A parameter and the token balances, it's finding the liquidity D that will satisfy this equation. And graphically, we can see this as finding the D parameter so that this pink curve will go through the token balances, which is represented in this blue point. The A parameter inside Curve V1's AMM equation controls how flat the curve is. For example, if we increase A, we can see that the pink line, which represents Curve V1's AMM curve, becomes more flat like the constant sum. On the other hand, when we decrease this A parameter, we see that the curve becomes more like the constant product, and when A is equal to 0, it matches the constant product curve. Let's take a look at how this A parameter is calculated inside Curve V1's AMM. The contract that we'll take a look at is called Stable Swap 3 Pool. This is a contract that is deployed on the mainnet, and it holds DAI USDC and USDT. The function that calculates the current A parameter is called _A. The owner of this contract can set a new A parameter. When a new A parameter is set, it doesn't take effect immediately. Over time, it gradually changes from the current A parameter to this new target A parameter that is set by the admin. So inside this code, you see T1 and A1. A1 is the new A parameter that is set by the admin, and T1 is the timestamp where this new A parameter will stay fixed. At and after the timestamp T1, this A parameter will stop increasing and it will stay flat as the new value A1. Let's say that the admin sets an A parameter to A1 at time T0. Then over time, from time between T0 to T1, the current A will gradually increase to A1. After time T1, since the current A parameter has reached A1, it will stay flat as A1. And we can see this in the code over here. If the current timestamp is less than T1, then get the A parameter, A0 that was set at time T0. And there are two cases. If the target A parameter A1 is greater than A0, or if the target A1 is less than or equal to A0. Both have a similar code, so we'll just take a look at when A1 is greater than A0. And to understand this code, consider the two cases. When timestamp is equal to T0 and when timestamp is equal to T1. Let's start with the case when timestamp is equal to T0. When timestamp is equal to T0, this expression T0 minus T0 is equal to 0. So when we multiply this part by 0, this whole expression will be equal to 0, so we get A0. On the other hand, when timestamp is equal to T1, then this part of the code is equal to T1 minus T0. Divided by T1 minus T0 is equal to 1. So this part of the code will be A1 minus A0 multiplied by 1, which is simply equal to A1 minus A0. And then let's now do this A0 plus A1 minus A0. The A0 cancels out with this A0 over here, and we get back A1. At time T0, we see that the A parameter returns A0, and at time T1, the A parameter returns A1. And anywhere in between this blocked out timestamp minus T0 divided by T1 minus T0 is a fraction that is less than 1. So the A parameter that is returned will be some number between A0 and A1. And that's how this part of the code works. This part of the code works almost exactly the same, except the current A parameter gradually decreases to the new parameter A1. Otherwise, if the current timestamp is greater than or equal to T1, then it returns A1. So that is how the A parameter is calculated. Next, let's take a look at how the admin can set this A parameter. The function that the owner of this contract can call to set the A parameters are rampA and stopRampA. Let's first take a look at the function rampA. What this function does is set the future A parameter. In the code that we saw previously, this will set the parameter A1. For the input, it's going to take in the future A and future time. First, it checks that message sender is the owner of the contract, and then it checks that the current timestamp is greater than or equal to initial A time plus min ramp time. This initial A time is set every time this rampA function is called. So once you call rampA, this means that you'll need to wait some time, min ramp time, before you can call it again. And then it checks future time is greater than or equal to the current timestamp plus min ramp time. The next part of the code calculates the current A, and then it checks that future A is greater than 0 and also less than max. Next, it checks that the future A does not drastically change from the current A. If future A is greater than or equal to current A, then it checks that the future A is less than or equal to the current A times max A change. What you're seeing here is that future A is capped by some maximum A change multiplied by current A. On the other hand, if future A is less than the current A, then it checks that the future A is greater than or equal to the current A divided by max A change. In other words, future A must be greater than or equal to some fraction of current A. And this fraction is determined by this max A change. After all these check pass, it sets initial A to the current A, future A to the future A from the input, and sets the timestamps. So that's the function ramp A. Next, let's take a look at the function stop ramp A. And again, only the owner of this contract can call this function. And when this function is called, it gets the current A by calling self._A. This is the function that we took a look at earlier. And then it sets initial A, future A to the current A, and sets the timestamps. Thus the functions stop ramp A and ramp A. These are functions that the admin calls to set the A parameter. Inside Curve V1 AMM, all of the token balances are converted to have 18 decimals before any calculations are performed. Here we're looking at a contract for DAI, USDC, and USDT. DAI has 18 decimals, so there's no conversion to be performed to have 18 decimals. USDC and USDT both have 6 decimals. So the USDC and the USDT balance inside the pool must be converted to have 18 decimals. And this is done by an internal function called _XP. The naming convention is a little bit weird. The way I remember this is X being the token balances and P for precision. So what this function will do is convert the token balances inside this contract to have 18 decimals. Let's take a look at this function. First, it creates a UN256 array of size n, and it initializes two rates. And what is this rates? The rates I defined at the top of the contracts. The first entry is one with 18 zeros. The next two entries are one with 30 zeros. So let's go back to the function that we were looking at, _XP. Okay, going back to the function _XP, we know that here results is initialized to be an array of 1E18, 1E30, and 1E30. In other words, 1 followed by 18 zeros and 1 followed by 30 zeros. And then it runs a loop for I equal to 0 to n number of coins. This contract holds 3 coins, so this n coins will be equal to 3. The first coin is DAI, and the second coin is USDC, and the third coin is USDT. So for the first iteration, it says results of I. Initially, it will hold 1E18, so this number will be 1E18 times self.balances of I. Again, the first coin is DAI, so balances of 0 will hold the DAI balance locked in this contract. DAI has 18 decimals, and then it divides by lending precision. Let's check out what this value of the lending precision is. Okay, here it is. Lending precision is 10 to the 18. Okay, let's now see what the first iteration will produce. Results of I will initially hold 1E18, and then it's multiplied by the balance of DAI. Again, DAI has 18 decimals. And then lending precision is 1E18. So let's do the math. 1E18 times DAI balance divided by 1E18. This will be the DAI balance with 18 decimals. Okay, how about the second iteration? The second coin is USDC, and result of I is initialized as 1E30. So result of I will be 1E30. Self.balances of I will be the balance of USDC. Again, USDC has 6 decimals. And again, lending precision is 18 decimals. So for the second iteration, it will be 1E30, which comes from here, multiplied by USDC balance. USDC balance has 6 decimals, and then divided by 1E18. How many zeros will we have? We have 30 zeros over here. USDC balance has 6 decimals, so 30 plus 6 is 36 zeros, and then divided by 10 to the 18, so this will result in 36 minus 18, which is equal to 18 decimals. And the same goes for the last iteration, USDT. USDT has 6 decimals. Result of I is initialized as 1E30. So 1E30 times USDC balance, this will have 6 decimals. So this multiplication will result in 36 decimals divided by 18, and we get 18 decimals. So in summary, what this function does is it takes the token balances and then normalizes all the token balances to have 18 decimals. The variable D that you see over here, and over here inside Curve V1's equation determines the liquidity of the AMM. There is a special meaning to this variable D. The special meaning of this variable D is that when the pool is perfectly balanced, for example, let's say that we have a pool with 2 tokens, X and Y, and here we have D equals to 50. When the pool is perfectly balanced, then we will have half of this for each token. So for token X, since D is equal to 50 and half of that will be 25, and also for token Y, we will also have 25 tokens. So when the pool is balanced, we will have token X and token Y be over here when this value for D is equal to 50. This is an example of a pool with 2 tokens. If we have a pool with 3 tokens, then we would divide this D by 3. More generally, if we had n tokens, D over n will be the number of each token when the pool is perfectly balanced. Inside the stable salt 3 pool contract, the value D is calculated using Newton's method. As an input, it's going to take in XP that we covered in the previous video. As a reminder, this XP represents the normalized balance of tokens. In this contract, this normalized balance will have 18 decimals. DAI, USDC, and USDT will be normalized to all have 18 decimals. And then we also have this input called AMP. This AMP, when multiplied by n, will result in A times n to the n. We'll come back to this later. So inside this function, it's going to perform the Newton's method to calculate the value for D. The first part is to sum up all of the token balances that are normalized, and you can see this over here. Run the for loop for XP, which represents the normalized balance, and for each x, add it to a variable called s. If s is equal to 0, then we return D as equal to 0. Otherwise, we proceed. And then, this is the part that does the Newton's method. We can see that it runs the iteration for max 255. And at the bottom, we can also see that if the previous D preb and the current D is less than or equal to 1, which you see over here and over here, then we break out of the for loop. These two cases mean that D and D preb are close enough, so using Newton's method, it found the D that satisfies the Curve V1 equation. Inside the for loop, we can also see how this D is calculated. For each iteration, it will calculate D raised to the power of n plus 1. Since this pool has 3 tokens, you can think about n is equal to 3. And then divided by n raised to the power of m, multiplied by all of the token balances. And that's what this part of the code is doing. It's calculating this expression. And then moving on, next it calculates the next D using the Newton's method. Remember that for each iteration of the Newton's method, we calculate the next D to be equal to D minus f of D divided by the derivative of f with respect to D and then evaluate it at D. You can check for yourself that this code over here is equivalent to this equation. And I'll also link you to a Python code that I wrote that quickly checks that this code and this code are equal. Okay, moving on. Once this part of the code calculates the D for the next iteration, it checks this D with the previous D. And if the difference between this current D and the previous D is less than or equal to 1, then the for loop exits. Since at this point, we found a solution to D that satisfied the Curve's V1 equation. Also notice that even if it does not converge, so this part of the code never evaluates to true, then this for loop will run 255 times, and then at the end it will return D whatever this D is, even if Newton's method could not find a solution. And that completes the code walkthrough for the function getD. When I first saw the function getVirtualPrice, I didn't know what this function was doing. Does this function return the price of the tokens, or does it return the value of each LP tokens? But now we can figure out what this function does by looking at the code. In the previous video, we looked at the function getD. This function uses the Newton's method to calculate this value called D. And this D represents the liquidity of this AMM. When all of the token balances inside the AMM are equal, then the pool is perfectly balanced. And when the pool is perfectly balanced, and let's say that there are n tokens, then D over n will be the token balance for each token. So that is the meaning of D. So once we calculate D, next it gets the total supply. This total supply is the amount of LP tokens that were minted. And then when we look at this part of the code, we can figure out what this function getVirtualPrice does. It takes in D, so this is like the number that represents liquidity, and then times it by precision, and then divides by the total amount of LP tokens that were minted. So liquidity divided by the total amount of LP tokens. Effectively, this will give us the value of each LP token. So the function getVirtualPrice, we now know that it returns the value of each LP token. Once you understand what the value D represents, it's now difficult to understand what the function calcTokenAmount does. For the input, it's going to take in the amount of tokens and then a Boolean flag called deposit. If this is a deposit, then this will be true, otherwise it will be false. And then it returns a single number, uint256. But what does this number return? Does it return like the amount of tokens, or does it return like the amount of LP tokens to be minted or burnt? Well, the answer is it returns the amount of LP tokens to be minted or to be burnt. Now, this function does not take into account the fees that might occur for making the pool imbalanced, whether this is from adding liquidity or removing liquidity. So what this function does is it's a simplified calculation of amount of LP tokens that either will be minted or burnt for putting in or taking out this much amount of tokens. Let's take a look at this function. So first it gets the balance and then gets the A parameter AMP, and then it calculates this number D0. D0 is calculated from the current balance of tokens. Again, this number D represents liquidity. And then it's going to run a loop to modify this balances. If it is a deposit, then add the amounts from the inputs. Otherwise, if it is a withdrawal, if it is a remove liquidity, then from the current balance, take out this much amount. Then afterwards, after this balance has been updated, it calculates the value for D again. This is named as D1. Next, it gets the total supply, and then it calculates the difference of D1 and D0. If it is a deposit, then D1 must have increased. Since we're adding tokens, liquidity must have increased. Otherwise, if we're taking liquidity out, then liquidity must have decreased, so D0 will be greater than or equal to D1. Taking this difference, and then we multiply by the total supply of LP tokens, and then divide by the liquidity D0 before the balances were updated. In other words, this diff divided by D0 represents the ratio of change in liquidity, and then multiply by token amount to calculate the amount of LP tokens that either will be minted or will be withdrawn. To swap tokens with the Curve V1 AMM, a user will call the function exchange. For example, let's say that this user wanted to swap DAI for USDC from the StableSwap3 pool contract. First, they will call the function exchange, specifying that the token in is DAI and the amount of DAI to swap. The StableSwap3 pool contract will transfer the DAI in from the user over to the pool contract, calculate the amount of USDC to give back, and then transfer the USDC from the pool contract over to the user. Before we do a code walkthrough for the function exchange inside the contract StableSwap3 pool, I first want to outline the algorithm for the function exchange. Inside the function exchange, the first thing it does is it normalizes the token balances to all have 18 decimals. DAI has 18 decimals, however USDC and USDT have 6 decimals. To make the rest of the calculation easy, inside the function exchange, it will first normalize all of the token balances to have 18 decimals. This will create an array of token balances, which is initialized inside memory. Next, it will transfer the token in, and then update the token balance that was normalized in step 1. The normalized token balance in step 1 is in memory, so here we're updating that normalized token balance. Next, using the updated token balance, it will calculate the balance of token out. The calculation of token out balance involves several steps. Two of the steps that I want to highlight here is the calculation of the A parameter and the calculation of liquidity D. Once the new balance for the token out is calculated, we can now take the difference of the new token out balance minus the old token out balance to calculate the amount of token that will go out. In Curve V1, swap fees are taken out of token out. So the next step is to calculate the swap fee. Before transferring the token out, it will update the internal token balance. So this will be updating the state variables that keep track of the token balances inside the pool contract. And then finally transfer the token out. So this is the outline of the code for the function exchange. To swap tokens on Curve V1 AMM, you'll need to call the function exchange. It takes in several inputs, index I, index j, dx, and min dy. I is the index for the token that's going to come in, and j is the index for the token that's going to go out. dx is the amount of token to put in, and min dy is the minimum amount of token that you expect to get back, or else this function will fail. The function first creates an array called rates. Remember that for 3 pool, this rates is fixed to a constant of 1e18, 1e30, and 1e30. And what these numbers are used for is to normalize all of the token balances to 1e18. Okay, moving on. It stores the balances of the tokens, the actual balances of the tokens, so this will be DAI, USDC, and USDT, into memory called O balances. And then it takes the token balances and then normalizes it by calling the function _xp_mem. At this point, all of the token balance will be normalized to have 18 decimals. The next section of the code deals with bringing in the token in, transferring the token into this pool contract. It first creates a variable called dx with fee. This is used for tokens with fee on transfer. For example, some tokens, when they are transferred, does not actually transfer the full amount. Instead, it will take a fee for transferring that token. So the amount of token that will come into the pool with these kind of tokens will be less than the amount that was specified. So that is what this dx with fee is used for. This variable will become more clear as we go down further in the code. Next, it gets the address of the input token. This will be stored in coins of I. Remember, I was an input from over here that specifies the input token. So it gets the address of the coin that's going to come in. And if this input token has a fee on transfer, then what the pool contract will do is first get the balance before transfer, and then it will create the balance again after transferring. The difference will be the actual amount that came into the pool. For simplicity, let's say that there is no fee on transfer. Okay, so moving on. Next, it calls the function transfer from to transfer the token in. Now notice here that it's not using the ERC20 interface to call the function transfer from. Instead, it's using a low-level call to encode the function call and all of the parameters. Transfer from message.sender to this contract for the amount dx. The reason why it's using a low-level raw call to execute transfer from is because some tokens, like USDT, does not return a boolean when the function transfer from is called. And other tokens like DAI, when the function transfer from is called, it returns a boolean. And if we were to use the IERC20 interface that expects a boolean to be returned, and we call transfer from on USDT, then the function call to transfer from will fail. So this is why it's using a low-level call to avoid that error. It solves the problem of calling the function transfer from, both for tokens like DAI that returns a boolean, and tokens like USDT does not return a boolean. Okay, once transfer from is called, next it checks that if the response from this raw call returns anything, then it checks that the boolean is equal to true. And then we see dx with fee again. After calling transfer from, it queries the balance of tokens again, takes the difference to calculate the actual amount that came in. For simple tokens like DAI and USDT that does not have fee on transfer, you can think about this dx with fee as equaling to dx. The actual amount that was transferred into the pool is the amount that was specified. However, for tokens with fee, then we'll need to query the balance of the token before transfer from and also after transfer from to calculate the actual amount of tokens that came in. After the input token is transferred into this pool contract, next it does the calculation for the amount of token that will go out. First, to this XP, this represents the normalized balance of the tokens. It modifies the normalized balance of token in. To XP a buy, add dx with fee, and this dx with fee is also normalized to have 18 decimals. We can see this, that it is multiplied by rates a buy and then divided by precisions. This code will make sure that this part of the code has 18 decimals. Next, it calculates this pool's token balance of token out. In the previous step over here, because token came in, this new y that is calculated using Newton's method by calling the function getY, this y value must decrease from the previous value. We'll take a look at what this function does in the next video. For now, you can think about this function as, given that the index of token in is I and the index of token out is j, the amount that came in is x, the new balance of input token is x, and then the normalized balances are xp, then it calculates the new balance for token out. Since token came in, this new balance of token out must decrease, and we can see this over here. dy will be equal to the current normalized balance of token out minus the new balance of token out. And for a rounding error, it also does a -1. The difference, dy, is the amount of token that will go out. From the amount of token that will go out, the fee is calculated. This is called dy fee. And it's a simple calculation. Take the amount that is going out and then multiply by some ratio, fee divided by fee denominator. Next, it converts the normalized balance into the actual balance by reversing the operations. To normalize a balance, we multiply the token balance by rates of j and then divide it by precisions. To convert this normalized balance back into the real balance, we will multiply by precision and then divide by the rates. After we convert this into the real balance, it checks that this dy is greater than or equal to min dy. Next, it calculates the admin fee. This admin fee is a fraction of the dy fee. And then the last part of the code is to update the token balances. The balance of token in will be the old balance plus the amount that came in. And the balance of token out will be the old balance minus dy minus dy admin fee. This part is a little bit confusing, so I've unpacked what this actually does. dy, let's take a look at this. dy is equal to dy minus dy fee. And then dy admin fee is a fraction of this dy fee. This part of the code, what it actually is doing is this. Minus dy minus dy fee, and then minus dy admin fee. We can do the math, we can simplify the math, and this will be equal to minus dy, and then inside this parentheses, the minus and minus become a plus, so this becomes plus dy fee, and then we have minus dy admin fee. So what this is doing is taking the old balance minus the amount of token that will go out, dy, and not all of this dy is going out. Some of it will stay as fee that are given to the liquidity providers. So we keep this amount dy fee. But from this dy fee, we're also going to give it to the pool admin, so we minus dy admin fee. So this is what this part of the code is doing. And then the last part is to transfer the token for token out. And again, it's using raw call to call the function transfer to make sure that transfer does not throw any errors. And then it emits an event of token exchange. So that is the function for exchange. So we saw that the function getY calculates the token balance of token out if the new balance of token in is x. And this function is called inside the function exchange, which is called to swap tokens. Let's take a look at how this function getY is implemented. For the inputs of function getY, it takes in the index of token in, this will be I, and the index of token out, j, the new balance of token in, which is x, and then the rest of the token balances, xp. This xp represents the normalized balances. And then it's going to return a single value. This value will represent the new balance of token out. Recall that Curve's equation is a complex equation, and it's really difficult to get an explicit equation for token out. The way that Curve finds the amount of token out is to use Newton's method. So first, it does some checks on the indexes, and then moving on, it gets AMP. Next, it uses Newton's method to get D. This D again represents the liquidity of this AMM. And then there are a bunch of variables that are hard to guess what they're used for from their name. You have C, capital S underscore, and then later on in the code you'll see more. Basically, what they're used for is to calculate Newton's method, which we'll come back over here. So going back up, this C variable, you can later verify for yourself that this will turn out to be d raised to the power of n plus 1, where n is the number of tokens for this pool. For stable swap 3 pool, this n will be equal to 3. And then divided by this expression, n raised to the n times p, where p is the product of all of the token balances except for token j, which represents the token out. Multiply this p by a times n to the n. That's what this c will stand for. And then s underscore will be the sum of all tokens except for token equal to j, which is the token out. And then we have a and n, which represents a times n to the n. Okay, and the next part of the code, you can verify for yourself that it calculates c, which we see over here, to be this expression. And then moving on, we also calculate b, and this c and d, you'll see later that it is used to calculate Newton's method over here. And then the next part of the code is where it uses the Newton's method to find the value for y. For the initial guess of Newton's method, it uses the liquidity d. The for loop will run max 255 times, and then for each iteration, it will calculate y based on this equation, and you can verify for yourself that this equation is equivalent to the Newton's method, y minus f of I divided by the derivative of f with respect to y evaluated at y. I'll also link you to the code that I wrote in Python, which verifies that this code is equivalent to this equation. Then next it compares this new y with the previous y. If the difference between them are less than or equal to 1, then it found the solution, so it will return. Otherwise, it will run the iteration for 255 times, and then simply return y. If you wanted to know the amount of tokens that will come out from a swap with a Curve V1 AMM, then what function should you call? The function that you should call, which will calculate the amount of token that will come out if you were to swap with the Curve V1 AMM, is the function getDy and getDy underline. So there are two functions. The difference between the function getDy and getDy underline makes sense when the tokens inside this pool contract are yield bearing. For example, for 3 pool, the tokens are DAI, USDC, and USDT. If you were to hold these tokens, they will not give you any yield. So in this case, calling the function getDy and getDy underline give you back the exact same amounts. Now consider the case when the tokens inside the pool earn some kind of yield. For example, let's say that we have the tokens DAI and CUSDC. The token CUSDC is a token that you get for depositing USDC into a compound. This token is yield bearing. If you were to hold on to this CUSDC, over time you will earn some interest. And let's say that you wanted to find out how much USDC you will get for putting in DAI. But the pool tokens are DAI and CUSDC. So in this case, to answer the question how much USDC you will get for putting in DAI, you will call the function getDy underline. It will calculate, if you were to put in DAI, how much USDC, which is the underlying token for CUSDC, you'll get. But for stable swap 3 pool, the tokens are DAI, USDC, and USDT. So these two functions, getDy underline and getDy, are the same. So let's take a look at this function, getDy. For the input, it's going to take in the index of the token in and index of the token out, and the amount of token that you're going to put in, dx. And then it calculates the amount of token that the AMM will give you back. First, it gets the rates. Remember, for this stable swap 3 pool, this rates is a fixed number of 1E18, 1E30, and 1E30. Next, it gets the token balance, which are normalized to all have 18 decimals. The tokens are DAI, USDC, and USDT. DAI has 18 decimals, but USDC and USDT have 6 decimals. By calling this function, all of the token balances are normalized with 18 decimals. The next part of the code calculates the amount of token that will come out and the fees on token out. The first part is adding the amount of token in to the current balance of token in inside this pool. And this part normalizes the amount of token in to have 18 decimals. Next, it calculates the pool balance of token out if we were to put in dx amount of token into this pool. Remember that this function uses the Newton's method to calculate the new balance of token out. Since token is coming in, the balance of this token out will decrease, and taking the difference of the current balance of token out and the new balance of token out, and accounting for rounding errors, we also minus 1. Basically, this difference of old balance of token out minus the new balance of token out is the calculation for the amount of token that will come out. This is named dy. A fraction of this dy will be kept inside the pool as swap fee, and this is calculated by taking some fraction of dy. And the actual amount of token that will come out is dy minus the fee. So that's the function getDy. The first exercise in Curve V1 is to calculate the amount of token you'll get for putting in some amount of token. For this exercise, what you'll do is calculate the amount of USDC that you'll get for putting in DAI. And the amount of DAI that you'll use is 1 million DAI. And to calculate the amount of USDC you'll get for putting in 1 million DAI, you'll need to call the function getDy underline. If you need a refresher on how to call this function, you can check it out by going on the source, interfaces, curve, stable swap 3 pool, and look for a function called getDy underline. The inputs are the index for token in, index for token out, and the amount of token in that you're putting in. Let's go over the solution for exercise 1. Exercise 1 was to call the function getDy underline on stable swap 3 pool. So first, I'm going to check how to call this function getDy underline inside the interface. Here it is. So I'll copy this, and then I'll paste it here. And how do we call the curve stable swap 3 pool contract? Going up to the setup and above the setup, I can see that the curve 3 pool is initialized as a variable called pool. So the function that we'll need to call here is called pool.getDy underline, and then we'll need to pass in the correct inputs. The first input will be the index of token in. DAI has index 0. The next input will be the index of token out. USDC is index 1, since this pool is DAI, USDC, and USDT. And then the amount of DAI that we're going to put in. For this exercise, we're going to put in 1 million DAI. So this is 1E6. DAI has 18 decimals, 1E18. The function getDy underlying returns a single output called dy. So let's assign this dy to the output of calling the function pool.getDy underlying. I forgot to put a semicolon here, so I'll put a semicolon. Okay, and let's try executing exercise 1. Inside the terminal, I'll type forge test fork URL. This is an environment variable that contains my RPC URL. And then we'll match on path, match path test curve V1 exercises, curve V1 swap.test.sol. Furthermore, we'll also match on the test match test get dy underline. And then we'll print out the console logs -bbb. Okay, the exercise passed. For putting in 1 million DAI, this is the amount of USDC that we'll get. For exercise 2, actually swap the DAI for USDC. The amount of DAI that you'll swap is 1 million DAI. And as a setup, inside this setup, this contract is given 1 million DAI, and it has approved the Curve StableSwap 3-pool contract to spend all of the DAI. Here you'll need to call the function exchange to swap DAI for USDC. To call the function exchange, you can navigate to the interface called iStableSwap 3-pool, and the path to this is specified over here. Under source, interfaces curve iStableSwap 3-pool. And here's the function exchange. The inputs are the index for the token in, index for token out, amount of token that you're going to put in, and the minimum amount of token out that you expect to get back. So call this function to swap DAI for USDC. Let's go over the solution for exercise 2. Exercise 2 is to swap 1 million DAI for USDC on Curve V1. So the function that we'll need to call is pool.exchange. And what are the inputs that we need to pass into this function? Let's check the interface. And inside the interface, it's going to take in these inputs. I'll copy these inputs, and then we'll paste it here. And before I forget, I'll put a semicolon as well. Okay, so for the inputs, the first input is the index of the token that we're putting in. We're swapping DAI for USDC, and DAI has index 0. USDC has index 1. The amount of DAI that we're going to put in is 1 million DAI. 1E6 times 1E18. 1 million has 6 zeros, as you can see from here, and DAI has 18 decimals. 1E6 multiplied by 1E18 represents 1 million DAI. Okay, next, minimum DY. Minimum amount of USDC that we expect to get back. For this example, let's say 999,000. 999,000 is 0.999 times 1E6. 0.999 of 1 million is 999,000. And USDC has 6 decimals, so say 1E6. That completes exercise 2. Let's execute this test. Inside the terminal, I'll type forge test fork URL, match path, test curve V1 exercises curve V1 swap.test.sol, and the exercise that we're going to execute is called test exchange. Okay, and our test passed. For putting in 1 million DAI, we got 999,917 USDC. To add liquidity to a Curve V1 AMM, the user will call the function add liquidity. For example, let's say that a user wants to add liquidity to the StableSwap 3-pool contract. The StableSwap 3-pool contract holds 3 tokens, DAI, USDC, and USDT. The user will call the function add liquidity and specify the amount of DAI, USDC, and USDT to put inside the contract. Curve V1 allows the user to specify the amount of tokens to put in. In the example of StableSwap 3-pool, we have 3 tokens, and the user can specify the amount of any of this token to be equal to 0. For example, if they only wanted to put in DAI, they would put in some amount of DAI, and for USDC and USDT, they will specify 0. As another example, let's say that the user only wants to put in USDC and USDT. Then for USDC and USDT, they will specify an amount that is greater than 0, and for the amount of DAI, they will set it equal to 0. Next, the amount of tokens that the user specified is transferred into the StableSwap 3-pool contract, and the contract will calculate the amount of LP shares to mint to the user. Here, LP means liquidity provider. The owner of the LP shares will later be able to withdraw any of these tokens in exchange for giving the LP shares back to the pool contract. Let me quickly outline what's going inside the function add liquidity before we do a cold walkthrough of this function. The first part of this function is to calculate the imbalance fee multiplier. In Curve V1, users can specify the amount of tokens to add as liquidity. This can cause the token balances in the pool to become imbalanced. For example, in the case of 3 pool, let's say that there are 100 DAI, 100 USDC, and 100 USDT. And now a user comes in and adds 1 million DAI as liquidity. The resulting token balances will be 1 million and 100 DAI, 100 USDC, and 100 USDT. To discourage users from imbalancing the pools, there is an imbalance fee. If you cause the pool to become severely imbalanced, then you'll be charged a lot of fees. So the first step is to calculate this imbalance fee multiplier, which will later be used to calculate the imbalance fee. The next step is to calculate the A parameter, and then calculate the current liquidity. Inside the code, this is called D0. Now inside the function add liquidity, liquidity will be calculated several times. The first part is to calculate liquidity before adding in any tokens. The next part is to calculate liquidity again after adding tokens. And then the last step is to calculate liquidity after minusing the imbalance fees. We'll come back to this again. Moving on, next it transfers the tokens in. And then it will update the token balances. At this point, it doesn't touch the state variables. It caches the token balances in memory and then updates this balance in memory. And then, like I said before, it will calculate liquidity again. Inside the code, this is named D1. So here, D0 will be the liquidity before adding tokens, and D1 will be the liquidity after adding tokens. Once we have D0 and D1, next it calculates the imbalance fee. The updated token balances will be subtracted with the imbalance fees, and then next it will calculate the liquidity again, D2. This is called D2 in the code, and it will represent the liquidity after adding tokens and then subtracting imbalance fees. Next, it will update the token balances, and this time it is updating the state variables. So why is it updating the token balance in memory over here, but over here it's updating the state variables? The reason is to save gas. Whenever you read or write to the state variable, it is very expensive compared to updating some data inside memory. And then calculate the LP shares, the liquidity provider shares. And then finally mint LP. So that's the quick outline of the function add liquidity. When a user adds or removes liquidity in a manner that changes the current ratio of the pool balances, a fee is deducted for causing this change. This is called the imbalance fee. Here you're looking at the code for the calculation of the imbalance fee when liquidity is added. This block of code might be difficult to understand, and when I first saw this, I had to draw an example using paper and pen to see what's going on over here. So in this video, let's go through a visual example of how to calculate the imbalance fee. Let's say that we have a stable swap pool where the tokens are DAI, USDC, and USDT, with 100 DAI, 90 USDC, and 110 USDT locked in this pool. With this token balances, we calculate liquidity D. Let's call this D0. When we divide D0 by 3, this will give the token balance of each tokens when the pool is perfectly balanced. So when the pool is perfectly balanced, we should roughly have approximately 100 DAI, 100 USDC, and 100 USDT. Now to go through an example of imbalance fee, let's say that we added 300 DAI. So now the token balance of DAI is 400. When the pool is perfectly balanced with this new token balances, we should roughly have D1 over 3 amount of tokens. So the pool will approximately have 194 DAI, USDC, and USDT. The imbalance fee is calculated by taking the difference of the actual balances of the tokens with what Curve calls ideal balances. This ideal balances is calculated by comparing D1 and D0, liquidity before making some kind of change, and liquidity after making some kind of change. In this example, liquidity before was approximately 299, and after is approximately 581. When we divide liquidity after by liquidity before, we get a ratio, approximately 1.94. This will give us the percentage of how liquidity changed. In this case, it says that liquidity increased by 94%. The ideal balances are calculated by taking this ratio of the change in liquidity and then multiplying it by the previous token balances. In our example, before adding liquidity, we had 100 DAI. So the ideal balance of DAI, if we were to add liquidity, is that previous amount of DAI, 100, multiplied by this ratio, 1.94. This turns out to be 194. For USDC, the token balances has not changed. We take the previous token balance, 90, and then multiply by the ratio 1.94. And this turns out to be approximately 174. And we do the same for USDT. The previous balance is 110. We multiply by the ratio 1.94, and we get that the ideal balance of USDT is 213. The liquidity increased by 94%. So in the ideal situation, we should increase all of the token balances by 94%. But as you can see, in our example, this is not the case. And now moving on to the imbalance fee. Imbalance fee is calculated by taking the difference of the actual token balance and then taking a percentage of that difference as fees. So for example, the ideal balance of DAI is 194. The actual balance of DAI is 400. Taking the difference, we get the difference is 206. We do the same for USDC and USDT. For USDC, the ideal balance is 174. The actual balance is 90. Taking the difference, we get 84. And finally, USDT. The actual balance is 110. The ideal balance is 213. The difference is 103. And finally, moving on to the calculation of fees. For this example, let's say that the fee multiplier is 1%. Starting with DAI, we have that the difference is 206. Multiply this by the fee multiplier, 1%, and we get that we're going to charge 2.06 DAI as imbalance fee. For USDC, the difference is 84. 1% of 84 is 0.84. So from the token balance of USDC, we deduct 0.84. For USDT, the difference is 103. 1% of 103 is 1.03. So we deduct 1.03 from the balance of USDT. Now the imbalance fee does not actually transfer the tokens out of the pool. The actual token balances are still 400 DAI, 90 USDC, and 110 USDT. The token balances that you see over here are used for the next part of the calculation, calculating the final liquidity after taking into account the imbalance fees. Let's call this liquidity D2. In our example, we added liquidity, and this final liquidity is used in the calculation of minting pool shares. And of course, since we deducted imbalance fee, this final liquidity is slightly less than liquidity before subtracting the imbalance fees. If you are wondering how I was able to come up with the numbers that I used in this example, what I did was I wrote a Python script. Given the token balances and the amount of tokens to put in, it will calculate the liquidity before adding liquidity, after adding liquidity, the imbalance fees, and then the liquidity accounting for the imbalance fees. Next, I took these numbers and then plotted on a graph. Now, if you also want to experiment with this script, first go over to the project repo. And from here, click on a folder called Notebook. The code that you just saw is called Curve V1 Imbalance Fee. Now, to execute this script, you'll need to install Jupyter Labs and Python. The function add liquidity is called to add tokens into Curve V1's AMM. For the inputs, it's going to take in the amount of coins to put in and the minimum amount of LP token to mint. Mint amount. Next, it initializes some variables. Fees is an array that will be used later for imbalance fee. Curve V1 allows you to add liquidity in a way that makes the token balances imbalanced. For example, you can decide to put only one token in, or you can decide to put all tokens in. And when you add one token as liquidity, this will make the current pool balance imbalanced. So that is what this fees array is used for. We'll come back to this later. Next, we have a variable called _fee. This number is used to charge for the imbalance fee. If you take a look at this, it has a weird formula. Fee multiplied by n coins divided by 4 times n coins minus 1. Basically, what this does is it makes sure that when you add liquidity and then remove liquidity, it won't be like swapping tokens without any swap fee. Let me explain this further. Let's say that we have token X and then we swap and then we get back token Y. In this case, we will have a swap fee on token Y. Now in Curve V1, we can also add liquidity in such a way that makes the token balances of the pool imbalanced. For example, we can decide only to add one token. So let's say we add X token to the pool. X token, add liquidity. Now, Curve V1 also allows us to remove liquidity in such a way that makes the token balances of the pool imbalanced. So for example, after we add only one token as liquidity, let's say that we remove liquidity and we remove liquidity in another coin, say remove liquidity, and we request token Y out. So effectively what we did here was we put in X token and then we took out token Y. This is the same as swapping token X for token Y. Now, if you do not have fee on imbalance fee when we're adding liquidity, basically this allows us to swap tokens for free. And to make sure that this does not happen, this weird equation makes sure that when we add liquidity and then remove liquidity, it is basically like a swap. For the math for how to derive this part of the equation, I'll put a link in the course. So that's what this fee is used for. And then we get the admin fee and then calculate the underscore rate. Next, we get the total supply. This will be the total supply of LP tokens that I minted. And then we first calculate liquidity, D0. D0 will be the liquidity before we add any tokens into this pool. And we can see this over here. D0 is equal to get the mem with the old balances, where the balances are the token balances of this pool. And then we initialize the array called new balances, which is basically copying the old balances. The next part of the code deals with transferring in the tokens. So scrolling down, we can see that inside the for loop, we get the coins to put in as liquidity, and then we call the function transfer from, and notice that here we're using raw call. This is to go around the problem that USDT does not return any boolean when transfer from is called. If you were to use the ERC20 interface for transfer from, when we call transfer from on USDT, this part of the code will fail. So to avoid this problem, it's using a raw call to call transfer from. So for each iteration, it's going to transfer the tokens in. And then it updates this new balances. Remember, this new balances was initialized as old balances. So to the old balances, we add some amount, the amount that came in. And with this new balances, next we calculate the D again. This time it is called D1. Again, this D represents liquidity. We added some new tokens, and here what it's doing is it's asking, with this new balance, what is the new liquidity? The next part of the code is calculating the imbalance fee. Imbalance fee basically means that if we were to add tokens into this pool in such a way that does not change the token balance ratios, then we've added tokens in an ideal way. Otherwise, if the ratios of the token change when we add liquidity, then there is some kind of fee that we'll have to pay. So the first question is, well, what is the ideal balance to add as liquidity? And the answer is simple. We take the old balance and we look at D0. This will be the liquidity before adding liquidity. And then D1, this will be the liquidity after adding liquidity. D1 divided by D0 will be the increase in liquidity. So the old balance should increase by this much amount, D1 divided by D0. As an example, let's say that D1 is 110, D0 is 100. So D1 divided by D0, so the ideal new balance will be 1.1 times the old balance. Next, we calculate how much the new balance is off from this ideal balance. If the ideal balance is greater than new balance is a lie, then the difference is ideal balance minus new balance is a buy. Otherwise, it's the opposite. New balance is a buy minus ideal balance. Here, we're just getting the difference of ideal balance and new balance is a buy. And then fee will be equal to this magic number fee that we saw over here. And then multiplies it by the difference, and then divides it by the fee denominator. This is the imbalance fee that will be charged for each token. Looking at this equation, let's imagine the case that we added liquidity so that the difference will be equal to 0. This will mean that the new balance is exactly equal to the ideal balance. And when we execute this part of the equation, we see that the difference will be equal to 0, so the fee for adding liquidity, in this case, the fee will be equal to 0. The next part of the code is to update the balance of the tokens. The balance of the tokens will be the new balance, and then a fraction of the imbalance fee will be given to the admin. This is what this part of the code is doing. Take the imbalance fee, multiply by some ratio which are given to the admin. Here, admin means the owner of this contract. And then from this new balances, we minus the fees, and using this new balance, we calculate the liquidity again. This time we name it as D2. So what we did here was we started with the old balance, added the amount of tokens that came in, and then from there, we minus the imbalance fee to get new balances. And from this new balance, we calculate the liquidity again, D2. And the last part of the code is to mint LP based on the increase from D0 to D2. And you can see this over here. Token supply multiplied by D2 minus D0. That's the difference between D2 and D0, and then divided by D0. And then it checks that this LP amount is greater than the mint amount specified by the user, and then it actually mints the LP tokens. So that is the function add liquidity. There's one exercise to add liquidity to Curve V1. In this exercise, you'll add 1 million DAI as liquidity to Curve V1 AMM. For the setup, this test contract is given 1 million DAI, and it has approved the pool to spend all of the DAIs. To add liquidity, you'll need to call the function add liquidity on the interface iStableSwap3 pool. The function add liquidity will take in two inputs, an array of amount of tokens that you're going to put in, and the minimum amount of LP that you expect to get back. The tokens inside the pool are DAI, USDC, and USDT. The first element in this array will specify the amount of DAI to put in, the second element in this array will specify the amount of USDC to put in, and the last element will specify the amount of USDT to put in. So for exercise 1, call the function add liquidity to add DAI as liquidity to Curve V1. Let's go through the solution for exercise 1 of adding liquidity to Curve V1. The function that we'll need to call is called add liquidity. And how do we call this function? I'll navigate to the iStableSwap3 pool interface, and then this is the function that we'll need to call, so I'll copy this, and then we'll paste it here. And before I forget, I'll put a semicolon here, and the contract that we'll need to call, if I scroll up, the StableSwap3 pool contract is initialized as a variable called pool. So the contract that we need to call here is pool.addLiquidity. And then we'll need to pass in these parameters. Let's first create a uint256 array of size 3 with the balances of the coins to add as liquidity. Say uint256, size is 3, memory, and I'll call it coins is equal to. We're going to put in 1 million DAI, and the first element in this array represents the amount of DAI that we'll put in. Say uint256, 1e6 times 1e18. 1e18 because DAI has 18 decimals. Since we're only going to put in DAI, the rest of the numbers in this array will be zeros. uint256, 0, and uint256, 0. Okay, once we prepare the coins array, we can remove this part. And next, let's prepare min LP, the minimum amount of LP tokens to mint for putting in 1 million DAI. For simplicity, let's just put a 1 here. Okay, that completes the exercise for add liquidity. Let's try calling this function. Inside the terminal, I'll type forge test --fork URL from my environment variable, and then match path, Curve V1, exercises, Curve V1 add liquidity.test.sol. Okay, and then type BBB to see what console logs prints out. So now we've added liquidity. There are several variations to remove liquidity. Let's look at the first way by calling the function remove liquidity. Remove liquidity will burn the LP shares of the liquidity provider and then send back all of the tokens in the pool in proportion to the amount of LP tokens that they burnt back to the liquidity provider. For example, let's say that a user calls remove liquidity on the StableSwap3 pool contract. The StableSwap3 pool contract has 3 tokens, DAI, USDC, and USDT. The user will specify the amount of LP shares to burn. The StableSwap contract will calculate the amount of DAI, USDC, and USDT to give back to the user, burn the shares, and then send all of these tokens back to the user. The function remove liquidity is not difficult to understand. First, they will calculate the amount of tokens to send back to the user. Next, they will update the state variables that keep track of the token balances, and then transfer the tokens out, and then burn the amount of LP shares that the user specified. Another common way to remove liquidity is to call the function remove liquidity 1 coin. What this function will do is it will burn the LP shares of the user and then send back a single token that the user specifies. For example, on the StableSwap3 pool contract, let's say that a user calls remove liquidity 1 coin and then specifying some amount of LP shares to burn. And for this example, let's say that user wants all of their liquidity withdrawn in a single token, DAI. The stable swap contract will calculate the amount of DAI to send back to the user, and then transfer this DAI over to the user. In the examples that we looked at, the difference between this function and the function remove liquidity is that remove liquidity will send back all 3 tokens to the user. However, this function will send a single token that the user specifies. And in this case, the user specified that they wanted all of their liquidity withdrawn in DAI. The function remove liquidity 1 coin may be a little bit difficult to understand. So let me quickly outline what's going on inside the function remove liquidity 1 coin. The first step is to calculate the amount of token to go out. Inside the code, this is named dy, and it also calculates the imbalance fee. Now the function that calculates dy and the imbalance fee may be difficult to understand. This function is called calc withdrawal 1 coin. Here I'm going to mention 3 things that this function does. It will calculate the A parameter, and then it will calculate the liquidity D, and then it will calculate the imbalance fee. Since here we're removing liquidity as a single coin, this will have the effect of making the token balances in the pool become imbalanced. The next step is to update the state variables that keep track of the token balances, and then burn the LP shares that the user specified. The last step is to transfer the token out. There are several options when it comes to removing liquidity from Curve V1 AMM. If you wanted to remove liquidity in a balanced way, then this will give you back all the tokens in the pool proportional to your LP tokens. This function is called remove liquidity. The other 2 options are to remove liquidity, where you specify the amount of tokens to remove, and to remove only 1 coin as liquidity. The functions are called remove liquidity imbalance and remove liquidity 1 coin. Let's first take a look at the function remove liquidity. Again, as an input, it's going to take in the amount. This will be the amount of LP tokens to burn and the minimum amount of tokens to return. And what this function will do is it will take in your LP and then send you back all of the tokens inside the pool proportional to the LP tokens that you burned. First, it caches the state variable total supply. This will be the total supply of LP tokens, and then initialize the array called amounts and fees. When we remove liquidity by calling this function, there's no imbalance fee since all of the tokens will be removed in proportion to the LP tokens. And as you can see over here, it says that fees are unused. So there's no imbalance fee for this function. So inside the for loop, we can see that it calculates each amount to send by taking the balance of the coins, multiplying by the LP token to be burnt, divided by total supply. And then it checks that this value to be sent back to the caller is greater than or equal to the minimum amount specified by the caller. Updates the balance, and then stores this amount to be sent to an array called amounts_byte. Next is the part where it actually transfers the tokens to the message sender for the amount value, which is calculated over here. And then it burns the LP tokens, and then it emits an event called remove liquidity. So this is a function to be called if you wanted to just burn your LP tokens, and in return you will receive all of the tokens inside the pool in the ratio of LP tokens that you burnt. The function remove liquidity 1 coin is called if you wanted to withdraw your liquidity all in a single coin. For example, inside the stable swap 3 pool, the tokens are DAI, USDC, and USDT. And let's say that you provided some liquidity, and now you want to remove your liquidity. However, you don't want all 3 tokens, DAI, USDC, and USDT. Instead, you want your liquidity withdrawn in 1 token, let's say DAI. Then you will call this function remove liquidity 1 coin, specifying the amount of LP tokens to burn and the token that you want to withdraw. To calculate the amount of token that will be sent back to you, in our example, this token will be DAI. There's an internal function called calc withdrawal 1 coin, which will calculate the amount of token to send back to you. The code for this function may be a little bit difficult to understand. So before we do a code walkthrough, I first want to show you a geometric explanation of how this function calculates the amount of token that you will receive. Imagine that we have a Curve V1 AMM with liquidity equal to 20. So this will be D equal to 20. Let's say that the current token balance is over here, shown as an orange point. As a quick review, for our AMM, token balances must be a point on this blue curve. And currently, our token balances are over here. Next, let's say that we decrease the liquidity by 50%. Initially, the liquidity D is 20, and then we reduce this liquidity D to 10. The resulting curve is shown in pink. Now, ideal way to decrease the liquidity is to decrease the token balances by the percentage that the liquidity decreased by. For this example, we decrease the liquidity by 50%, from 20 to 10. So in this case, the token balances should also decrease by 50%. This applies both to token X and token Y. For this example, initially we had a token balance of X equal to 6.57 and Y equal to 13.52. The liquidity will decrease by 50%, so the ideal amount of token X to withdraw will be half of this. This is equal to 3.285, and so on. This is an approximation. And the ideal amount of token Y to withdraw is half of this number. This is approximately 6.76. When we do this, the resulting token balance will be over here, shown in green. Now notice that in this case, we withdrew 2 tokens. However, for remove liquidity 1 coin, we only want to withdraw in 1 coin. So on the graph, what would go on when we withdraw a token in 1 coin? So let's see what would go on here when we withdraw liquidity in 1 coin. For this example, we'll say that the token that we're going to withdraw is token Y. Token X is the horizontal x-axis and token Y is the vertical y-axis. So we're going to be decreasing the amount of token Y. Since we're not going to withdraw token X, the amount of token X should be the same. So we can represent this as a vertical line that goes through the current token balance of token X. Now recall that for AMMs, token balances must be on the curve that is defined by the AMMs equation. In our case, when we decrease liquidity, since we know what the amount of token X is, it must be somewhere on this line, then the only token balances that satisfies where the token X will be on this line, and the balance of token Y will be on this pink line, is the intersection between this green line and this pink line. This point shown in orange will be the actual token balance after withdrawing liquidity only in a single token. The amount of token X remains the same. Since we're not withdrawing token X, we're only withdrawing token Y. So the balance of token Y decreases. This difference between the original balance of token Y and the new balance of token Y that is calculated by the function calc_withdraw1coin, taking the difference will give us the amount of token Y that the user will receive. And of course, from this amount, fees will be deducted. Another function that you can call to remove liquidity, and if you wanted to remove liquidity in 1 coin, then you would call the function remove liquidity 1 coin. For example, inside the StableSwap3 pool, the tokens are DAI, USDC, and USDT. If we call the function remove liquidity, then it will give you back all 3 tokens. However, let's say that you wanted to just withdraw in USDC. Then you will call remove liquidity 1 coin and then specify the token that you want to withdraw. For the inputs, it's going to take in the token amount. This will be the LP token to be burnt. And then it's going to take in the index of the token to withdraw and the minimum amount of token that you expect to receive. And based off of this token that you want to receive, it calculates DY. This will be the amount of single token that you will receive. And this calculation is done by an internal function called calc_withdraw1coin, which we will take a look at in the next video. Checks that this DY is greater than or equal to minimum amount specified by the user, updates the token balances, minus DY from the current balance of tokens, and also a fraction of DY fee is given to the admin, so we also minus this from the current balance. Burn the LP tokens, send the tokens by calling the function transfer, and then that completes the function remove liquidity 1 coin. One thing to note here is that remember that when we add liquidity, there was an imbalance fee. And now we have this function called remove liquidity 1 coin, which will allow us to remove liquidity for 1 coin. So if we do add liquidity with 1 coin and then remove liquidity with another coin, this is like swapping a token. And if there wasn't any imbalance fee, then this is like swapping without any swap fees. So that is why there's an imbalance fee when we add or remove liquidity in a way that makes the token balances in the pool imbalanced. Inside the function remove liquidity 1 coin, there's an internal function called calc_withdraw1coin, which will calculate the amount of single token that you will receive for burning this much amount of LP tokens. Let's take a look at how this function is implemented. As a note, there's also an external function that calls into this internal function calc_withdraw1coin. Given the LP amount and the token that you want to receive, it will calculate the amount of token that you will receive for burning this much amount of LP tokens. Okay, here's the internal function calc withdraw OneCoin. For the inputs, it's going to take in the LP amount and the token that you wish to withdraw. For the output, it's going to calculate the amount of token that you will receive and the fees. The first part is to get the A parameter, and then next it initializes the variable that is used for the imbalance fee. It creates an array called precisions, caches the total supply of LP tokens, and then gets the balance of tokens that are normalized to all have 18 decimals, and then it calculates the liquidity D0. The next part of the code deals with calculating the imbalance fee. First, it calculates the ideal liquidity D1 if we were to burn this much amount of LP tokens, given the total supply. The liquidity will decrease by this LP amount to be burnt divided by the current total supply of LPs. For example, let's say that D0 is 100. And let's say that we have 10 LP tokens. And again, this D0 will be 100. And let's say that we have also 100 LP tokens. What is the percentage of LP tokens that we're burning compared to the total amount of LP tokens? Well, this is 10 will be the amount of LP tokens that we're burning, and total supply will be the total amount of LP tokens. 10 divided by 100 will be 0.1, which is equal to 10%. So what this part of the code is doing in this example is we're taking 10% of the current liquidity and then subtracting it from the current liquidity. 10% of the current liquidity, 100, will be 10. 100 is the current liquidity. 100 minus 10 will be 90. In this simple example, D1 will be equal to 90. Next, we initialize an array that will be used to calculate the imbalance fees. First, we take D1. This is the current liquidity reduced by the amount of LP tokens that we're burning. And then we use a Newton's method called getYD to calculate the new Y. Since the liquidity D1 is less than the liquidity D0, when we calculate the new Y with D1, this new Y will be less than the current Y. To further explain, let's say that we have a perfectly balanced pool with 3 tokens, X0, X1, and X2, all having 100 tokens. And let's say that the liquidity is D0. Since this is a balanced pool, all of the token amounts will be D0 divided by 3. So D0 divided by 3 will all be equal to 100. After reducing this current liquidity D0 by the amount of LP tokens that we're burning, let's say that if we were to remove liquidity in a balanced way, then D1 will be over here. So from token X0, we will remove this much amount of token X0. For X1, we will remove this much amount of X1. And likewise, for X2, we will remove this much amount of X2. All of these amounts that we're going to be removing are the same. So this is the ideal D1 over 3. Why is it 3? Well, because we have 3 tokens. However, inside this code, we're saying that we only want to remove one of the tokens. Let's say that the token that we want to remove is X1. So keeping the token balance for token X0 and token X2 the same at 100 and 100, we're going to remove only X1 until the new liquidity is D1. If we were to remove tokens in a balanced way, then the amount of tokens after removing will all be over here. However, since we're removing only one token and the rest will stay the same, this new Y, which represents the new token balance for X1, will be lower than D1 divided by 3. So keep this in mind as we go down further in the code. We calculate new Y, and first we calculate the difference, and it's called dy0. The difference will be the current token balance, XP of I, minus this new balance, which was calculated from above. The next part is to calculate the imbalance fee. It runs a loop for each token. If j is equal to the index of the token that we're removing, then the difference from the ideal amount of tokens to remove is XP of j will be the current balance of token that we're removing, and the liquidity will decrease by D1 divided by D0. So this will be the ideal amount of token balance after removing. However, the actual amount that we're removing is this new Y. Taking the difference, this will give us the difference from the ideal balance after removing liquidity and the actual amount after removing liquidity. Otherwise, for j, if j is not equal to the token that we're removing, the ideal balance is again given by XP of j times the decrease in liquidity, D1 divided by D0. The actual amount will be XP of j since we're not removing any tokens from these tokens. Once we calculate this difference from the ideal balance and the actual balance, we multiply this by the fee to calculate the imbalance fee. Once the imbalance fees are calculated, the next part is to calculate the actual amount of tokens that will leave this pool. And this is calculated by taking the token balance after the imbalance fee, and then calculating the new balance of token that's leaving by using the token balances with the imbalance fees subtracted. Taking the difference, this will give us dy, the actual amount of tokens that will come out of the pool, -1 accounting for rounding errors, and then return the actual amount to be sent and the imbalance fee on this token. So that is a function calc withdraw with 1 coin. There are 2 exercises to remove liquidity from Curve V1 AMM. For the setup, the test contract is given 1 million DAI, and it has put this 1 million DAI as liquidity to Curve V1 pool. So at this point, you'll have some LP tokens. The LP token is called Curve 3 CRB. For this test, the variable name for this Curve 3 CRB is LP. You'll be using this to remove liquidity. For the first exercise, call the function remove liquidity. Remember that the function remove liquidity will burn your LP tokens and give you back all of the tokens in the pool. For the StableSwap 3 pool, the tokens are DAI, USDC, and USDT. So after you call the function remove liquidity, you'll get DAI, USDC, and USDT. For this exercise, call the function remove liquidity. And you'll need to specify the amount of LP that you're going to be burning. The balance of the LP token inside this test contract, since LP is a IERC20, you can get the balance of LP tokens locked inside this contract by simply calling balance of, passing in the address of this contract. Once you get the LP balance of this contract, call the function remove liquidity, passing in the amount of LP. For this exercise, you'll be removing all of the LP tokens, and then the min coins, the minimum amount of coins that you expect to get back when you burn some amount of LP. For simplicity, you can put this min coins as 0 or 1, or whatever you want. There are 2 exercises to remove liquidity from Curve V1's AMM. The first exercise is to call the function remove liquidity. First, let's check how we will call this function. Inside the interface iStableSwap3 pool, I'll copy this function declaration and then paste it here. And I'm also going to check the name of the variable that is initialized for the Curve V1's pool. The name of the Curve V1's pool is called pool. So over here, I'll call pool.remove liquidity. And now we need to figure out the balance of LP that is locked in this contract and the minimum coins that we expect to get back. Let's start with the first one. How will we get the balance of LP tokens that is locked inside this contract? Let's check the setup. Looking at the setup, we added liquidity to this Curve V1 AMM, and the LP token that we get back is called LP. So, and it's also a ERC20 token, so we can get the balance of LP tokens inside this contract by calling lp.balance of address this. Let's store this into a variable, uint 256. I'll call it lp val, and then we can put it in here, lp val. Okay, the next part is to prepare this minimum coins array. Say uint 256 of size 3, memory, I'll call it min coins is equal to. For this exercise, let's keep it simple and just put a 1. Uint 256 1, uint 256 1, and uint 256 1. Okay, and then call the function remove liquidity with lpval and min coins. That completes the first exercise for removing liquidity from Curve V1. Let's execute the test and then call the function test remove liquidity. For this exercise, there is a function called test remove liquidity and test remove liquidity 1 coin. Before we execute the test for exercise 1, I only want this test remove liquidity to match exercise 1. So I'll put in a regular expression to say that we only want to match test remove liquidity. Do that by putting a backslash, opening parentheses, backslash, and then closing parentheses, and then execute the test. Okay, and our test passed. When we called the function remove liquidity, it gave us back all 3 tokens. We got approximately 368,000 DAI, 373,000 USDC, and 257,000 USDT. For the second exercise of removing liquidity from Curve V1, call the function remove liquidity 1 coin. This function will remove liquidity in a single coin that is specified by the caller. In this exercise, you'll take the LP token, burn all of the LP token, and then withdraw all of your liquidity in DAI. Inside the setup of this test, it adds liquidity, so this contract already has some LP tokens. This LP token is a ERC20 contract, so you can get the balance of LP tokens locked in this contract by calling balance up. And the function that you'll need to call is called remove liquidity 1 coin. Passing in the LP amount, this amount will be the LP balance locked inside the test contract. Specify the index of the token that you're withdrawing. Inside the stable swap repo, DAI has index equal to 0. And then the minimum coin, minimum amount of DAI that you expect to get back. For this exercise, we'll keep it simple, and you can put in 0, 1, or whatever number you want to put in. Okay, let's go over the solution for calling the function remove liquidity 1 coin. I'll navigate to the interface, and then copy this remove liquidity 1 coin, paste it here, put a semicolon, and the contract that we'll need to call is pool dot remove liquidity 1 coin. The first input is the LP balance. The LP balance inside this contract, let's call this uint256 LP bal is equal to, the contract is LP, and then it is a ERC20, so we can call balance of address this. Replace this LP with LP bal. For this exercise, we're going to remove DAI, so the index of DAI is 0. And for min coin, let's just set it to 1. Okay, so that completes the exercise. Let's try executing the test. Inside the terminal, I'll execute the similar command from the previous exercise. I'll modify the regular expression to match the test. Test remove liquidity underscore 1 coin. Okay, and our test passed. Unlike the previous exercise, notice that the only token that we got back is DAI, and we got back approximately 999,905 DAI. We received 0 USDC back and 0 USDT back.